I want to start today by going back and revisiting some of the conceptual things about gases and talk about kind of how they behave, and then we can do some more math. So what I've got on the board here is a description of an ideal gas. This is actually called the kinetic molecular theory of ideal gases. And there are 6 statements here, and we'll be going through those one at a time so that you can think about how gases behave. Now, surprisingly, real gases do behave pretty much like ideal gases as long as they're under normal conditions. Now, if you get them super, super cold, like down near absolute zero, they're not going to behave ideally. And if you get them under too much pressure, they're not going to behave ideally. But most of the time, they do behave like ideal gases. And because of these characteristics, then we can have some more laws that we can use mathematically. So let's look at this first one. It says gases are made of tiny particles, each of which has mass. And we've talked about that before. That's why we have air pressure, because we have gravity pulling down on these particles. That's why we have pressure in a container, because we have particles banging around. Now, in class, we took a balloon and we weighed it empty, and then we blew it up and weighed it again and saw that it actually has more mass when it's blown up. And you would expect that if you are putting particles that have mass into the balloon. So this might seem perfectly obvious to us, but there was a time when people didn't understand that gases were made of particles and had mass. They thought gases were some sort of, I don't know, I'm going to say fluid, but we have a different word for fluid today, but that they were not actually made of matter. But we know today that they are. So they're made of matter just like liquids and solids are, even though we can't see them. Number 2, the distances between the particles are very large compared to the size of the particles. Now this is important because this is why gas particles don't really interact with each other. We have these huge distances between them, and so occasionally they might bump into each other and kind of collide and bounce off, but they don't have a lot of attractions between them, and that's going to kind of get into another one down here, number 4. They don't exert forces on each other because compared to the size of the particles, they're super far apart, and that's why you can compress a gas. So if you put a gas into something like a syringe, and we did this with the Boyle's Law lab, you might remember. You put and then you piled the books on it, and you made the volume get less and less and less. You know, if you put water in that syringe, you wouldn't have been able to do that because the particles in water are very close together, and the particles in solids are very close together. But the reason that you could do that with gases is because the particles are so far apart that there's plenty of room to compress them. Number 3, the particles are in constant, rapid, random motion. Now, that's important to even have gas pressure. If we had a container where the particles were not moving, they would just be sitting on the bottom of the container, and we wouldn't have pressure because they wouldn't be banging against the sides. Now, how do we know particles of gases are in constant, rapid, random motion? Well, for one thing, diffusion. Think about this. Have you ever walked into the house where you live? So you open the door, you walk in, and you immediately know what's baking in the kitchen. So you know what's for dinner. Now, you might be happy about that or not happy about it, but you know. Why do you know? Because the molecules are coming out of the oven and they're moving all through the house. And you can smell them. Now, if the particles were not in constant, rapid, random motion, we would not have diffusion of gases like that. And maybe you've been in a place where somebody, well, actually sometimes the hallways at school are like this. Somebody puts on way too much cologne, or they spill some of it. That happens all the time in the freshman hallway, I've noticed. And then pretty soon the whole upstairs of building 2 smells like whatever cologne that was. Or on the days when the freshmen are dissecting minks. And you might remember this from last year. You would walk up the stairs and you would know already what we're doing today because you would be able to smell it. And that's because the gas particles that are coming off those minks are traveling all through the hallways. So we know that gas molecules move really fast because if they didn't, they wouldn't be traveling all over the place. We wouldn't have gas diffusion, and we wouldn't be able to detect them with our noses. The particles do not exert any forces on each other. And that this is true for an ideal gas. Now, in a real gas, sometimes there are some forces, and so sometimes the behavior of a real gas might not be exactly like an ideal gas. But the whole reason the thing is a gas is because the particles are not really attracted to each other. If they were attracted to each other very much, you'd have a liquid instead of a gas. Collisions are perfectly elastic. Okay, what that means is that when a gas molecule bumps into something, it doesn't lose any energy. Now, think about a rubber ball. Pretend I have a rubber ball in my hand. I drop the rubber ball. Picture in your mind what happens. You know what happens, right? It bounces kind of high the first time, not so high the second time, and eventually it's laying on the floor. Well, if gas molecules did that, all our gas molecules would be laying on the floor and we wouldn't be breathing. So obviously gas molecules don't do that, and they bounce off the walls and they bounce off each other and they don't lose any energy. So that's what we call elastic collisions. And the kinetic energy depends only on the temperature. This, by the way, is not only true of gases, this is true of liquids and solids as well. The amount of kinetic energy that particles have, and by particles we mean molecules, atoms, ions, whatever, only depends on the temperature. Temperature really is just another word for kinetic energy. Now, it doesn't mean that every single gas particle in this container has the exact same amount of kinetic energy. Temperature is an average. So if we took all the particles in here and took their average kinetic energies, that's related to the temperature of the gas. And if we raise the temperature, then the average kinetic energy goes up. And that's the only thing it depends on, is the temperature. So now that we know that, let's do some erasing here. And I want to introduce you to something called Avogadro's Law. And Avogadro's Law is a direct result of the fact that the molecules don't exert forces on each other. And in a sense, that means they don't recognize each other. So one gas molecule is as good as another gas molecule. They're all in there just bouncing around, and it doesn't matter what gas you have. So Avogadro's Law says that, if I can quote it here, at the same temperature and pressure, equal volumes of gases contain the same number of molecules. So what that says to us, let's say that we have two, now we're going to have to pretend because I don't draw that well, but let's just say that these two containers are the same volume. So here we've got these two gas containers, they're all sealed up and they contain some amount of gas. And we'll say that they have the same temperature and the same pressure. And therefore, we know that they have to contain the same number of molecules, even if they're two different gases. And this is called Avogadro's Law. Now, this is not necessarily intuitive. For example, I might be tempted to think that if I had hydrogen over here, which is very small particles, compared to something like argon over here, which would be much bigger particles, I might be tempted to think that if we have the same pressure and the same temperature and the same volume, that there would need to be fewer of the big molecules. That's what I might be tempted to think. But Avogadro's Law says absolutely not. The size of the particles is so tiny compared to the spaces between them that it doesn't even matter if this particle is bigger than this one. It's negligible compared to the size of the spaces between them, so it doesn't matter at all. We could have a mixture of gases over here and a single gas over here. It doesn't matter. The same number of molecules are going to be present if we have the same temperature and the same pressure. Now, a related idea is something called Dalton's Law. And once we have accepted Avogadro's Law, Dalton's Law becomes kind of intuitive. Sometimes this is called Dalton's Law of partial pressures. let's see, I'll give it to you mathematically and then I'll kind of explain what's going on here. So this P sub T will stand for the total pressure in the container. And Dalton's law deals with a situation where we have a mixture of gases, like normal air, for example. And this is going to be equal to the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3. And then sometimes we do that, P to the N. In other words, it doesn't matter if you have 10 or 20 gases mixed together in there. Each individual gas will exert some amount of pressure, and that's called its partial pressure, because it's not the total pressure, it's just the pressure from that one gas. And then there is obviously a total pressure in the container. So what Dalton is telling us is that all the individual pressures from all the individual gases add up to the total pressure, and that seems pretty much obvious. But another part of his law says that, and each individual partial pressure is proportional to the number of molecules of that gas. So, what does that mean, you might ask? That means that let's say that we had a mixture that was 50% argon and 50% neon. Okay, so only two gases and they are available in equal amounts. And let's say that the total pressure in the container was 10 atmospheres. So if you are told that, then you automatically know that because these are present in equal amounts, their partial pressures are equal. So that would mean that the partial pressure of argon is 5 atmospheres, the partial pressure of neon is 5 atmospheres, and they add up to 10. Now, what happens if we change this? Let's say that it's 75% argon and 25% neon. Well, that would tell us that argon is exerting 75% of the pressure. If it's present as 75% of the total number of molecules in there, or atoms in this case, it's also exerting 75% of the pressure. And therefore, the partial pressure of argon would be 7.5, and the partial pressure of neon would be 2.5. And we would say like this. So the pressure of argon, so with that little subscript, that means it's the partial pressure only of that one particular gas. So the partial pressure of argon is 7.5 atmospheres, and the partial pressure of neon is 2.5 atmospheres. And if we add those together, we get the total of 10 atmospheres. So it's always like that. And if you think about our regular atmosphere that's around us all the time, I don't know if you know this, but 78% of the atmosphere around us is made of nitrogen. And that's kind of important because nitrogen is not reactive at all. So if we had an atmosphere that was totally oxygen, everything would be catching on fire all the time, and everything would be reacting and oxidizing, and it would be a very unsafe environment because oxygen, believe it or not, is toxic if you have it in levels that are too high. Very reactive. It's only 21% oxygen. And you can see that that doesn't add up to 100, so we have 1% that's kind of a mixture of carbon dioxide and argon, believe it or not, is the other two important gases here, and a little bit of other things. But these are the two major gases in our atmosphere. So what that would mean is that if we have normal atmospheric pressure, where we have about 1 atmosphere of pressure around us all the time, that would mean that that's P total, that would mean that the partial pressure of nitrogen is 0.78 and the partial pressure of oxygen is 0.21. And those are going to add up to not quite 1 atmosphere because there are a couple of other gases in there. But that's the way that works. So the amount of pressure exerted by the gas is proportional to the amount of molecules of that gas that are in the container. And hopefully that makes sense. And now we have got, let's see, one more equation, and this is called the ideal gas equation. And remember that we have already talked about Boyle's law and Charles' law, and those kind of have some restrictions on them. Like you can only use Boyle's law if the temperature is not changing, and you can only use Charles' law if the pressure is not changing. But what if everything's changing? So now we need a law that we can use even if everything is changing. And that happens to be called the ideal gas law. And the ideal gas law says PV, and we're familiar with these, we've been using pressure and volume all along, equals nRT. All right, so pressure and volume we're already familiar with. And temperature we're already familiar with. Now, N is the number of moles of a material. We have not learned about moles yet, but for now, let me just tell you that it has to do with the number of molecules. What you are familiar with is a concept like a dozen. If I told you there are a dozen molecules, you would know right off the bat that that means there's 12 of them. Well, 12 isn't a very big number. When we're working with molecules, we need something bigger. So we use a mole. And a mole is 6.02 times 10 to the 23rd molecules or atoms or whatever. We should probably just say particles there. But anyway, it's a number of particles. So rather than trying to make a number here that's the actual number of molecules, what we do is sort of bundle them up. It's as if you had, I don't know, hundreds of eggs. And rather than trying to sell them as individual eggs, we box them up in packages of a dozen. And usually if you were to ask somebody how many eggs do you have in the case over there, they would say, well, we have 45 dozen eggs. They wouldn't tell you the individual number of eggs. And we use that same kind of strategy when we talk about molecules and atoms, because it's silly to try to give a number of the actual molecules. So since they're so tiny, we have, instead of 12, we have a really big number, but that's okay. So it's sort of like packaging them up in groups. And we will talk about that a whole lot more in the next unit. But N stands for the number of moles. And then R, this is a constant. And this constant has quite a few different values depending on what units you're using. You can imagine that if you are using different units of pressure and volume, that this constant would have to change. But just for the sake of simplicity, we're going to stick to one set of units so that we can stick to one gas constant. And the gas constant is 0.08206. Now I'm about to give you the units for the gas constant. This is not an equation. People get really confused by that sometimes. This is not an equation. It's units for the gas constant. Liter, atmosphere, moles, kelvins. So just like sometimes if we were measuring speed, we would have meters per second. If we're using a gas constant, we have liter atmospheres per mole Kelvin. All right, so this is all one unit. And this tells us what kind of units we have to use for everything else. So for pressure, we're going to have to use atmospheres. For volume, we're going to have to use liters. For temperature, we're going to have to use kelvins. No surprise, we have to use that all the time when we're doing gases. So now we have this handy equation that we can plug things into. So if you are given any combination of these variables and you only don't know one of them, you can just plug the numbers in and solve for the other one. So that is the ideal gas law, and we'll be using that to do some problems in class.